Um, the first thing, of course, is to convince ourselves that this is an important topic. And I think probably we all agree that it is. But one fact that I'd like to highlight is that the Texas Transportation Institute has calculated that more than half of all delays in U.S. urban areas are due to non-recurrent events that are more or less unpredictable from the point of view of travelers, which means that the cost of travel time variability to travelers will be correspondingly large. It's really a major thing. And the projects that we are evaluating will have consequences for the amount of travel time variability that travelers experience, which means that if we account for travel time variability, we'll get another ranking of projects than if we do not. And of course, then we should account for travel time variability. It's important, and it would influence the ranking of projects. So what we need to do that is first to define what it is that we're talking about, and this is my topic for today. Then we need to put numbers on it. So we need a unit of measurement. Then we need a value per unit, and then we need predictions of the quantity of travel time variability that exists and how it will change as a result of projects. Yeah. Okay, so I was told to assume that you have all read the paper, so I will not go through that in detail, but just say that we do have a theoretical foundation for talking about travel time variability in scheduling models. And these are models that describe travelers who care about when they travel. In general, they like to depart as late as possible and arrive as early as possible. And then we have the trade-off, and they are assumed to make optimal decisions in the face of travel time variability. And then there are lots of models that are possible, but a few of them lead to simple conclusions, and those are the models that we focus on. And what comes out is that in the simplest models, what we can either use as our unit of measurement is the variance of travel time or the standard deviation. So far, the variance has not been used much. Mostly, people have used the standard deviation or equivalent measures. And there has been some discussion about which measure to use, discussing measures that are essentially equivalent, including the measures mentioned here. So instead of the standard deviation, we could consider the difference between two quantiles in the travel time distribution, or the difference between a quantile and the mean travel time, or the buffer time index, or we could compute the mean lateness, so the average time later than something. But what turns out is that all these measures are proportional to each other when the shape of the travel time distribution is constant. So we can shift the mean, we can allow the standard deviation to vary, but if the underlying shape is constant, or more or less constant, then these measures are equivalent. So, which means we can pick any of these definitions that we like or think we are better able to communicate, and just use that, knowing that we have support in the same theory that leads to the standard deviation. So comparing these two simple measures that we have to choose from, they're based on different descriptions of the preferences of travelers regarding when to depart and when to arrive. And we have the step model and the slope model. And they just describe different behavior, different preferences. we have found that the step model, which is the most common, applies better, explains better the behavior in stated preference exercises of travelers who have fixed arrival times. So these are school teachers or workers with a sharply defined work start time, whereas people like us are perhaps better described by the slope model, and then the more appropriate measure for us would be the variance of travel time. So these are people who have some flexibility with regard to when they should arrive at work. For the standard deviation in this model, it turns out that the value of standard deviation depends on the shape of the travel time distribution, which is sometimes a complication and sometimes it's overlooked. So I'll talk a bit more about that later. A very attractive property of the variance is that we can just compute the variance of any travel time distribution, measure the value to travelers, and then transfer that value directly to other contexts where the shape of the travel time distribution changes, because the value is independent of the shape of the travel time distribution. Another advantage of the variance is when we work with network models, where we compute the generalized travel cost link by link, then it's very convenient if these costs can be added up in a consistent way. That's the case for the variance if we're prepared to assume that travel times are in practice independent across links. Then it's really easy to use. The standard deviation is not additive in the same way. Under independence, it's far from additive. So going a bit into the details of the value of standard deviation, in the step model, it has this form. So there's a first term beta plus gamma, which is just parameters from, so it's preference parameters. Then the second term is this integral, which is an integral of the inverse of f, which is the shape of the standardized travel time distribution. And it's through that term that this measure captures, for example, the skewness of the travel time distribution. So if we compare two situations where the skewness changes, where perhaps we make the extreme events more or less extreme, that will impact the shape of the standardized distribution, and through that the value of standard deviation. That term also means that if we decide to base a measure of travel time variability on this theoretical model, then we should adjust the value of standard deviation when we transfer the value from one context to another. So it may be that we have measured the value of standard deviation from SP data, where we have presented people with some travel time distribution, and that's where we measure our value. Then when we want to transfer that value to an RP context where there's a different travel time distribution, then we need to correct for that. And that comes straight out of the model, how to do that. Oops. Okay. I have, based on this, I have a couple of comments on what we'll see later from the Netherlands. So in your paper you write that you chose the standard deviation because it was more convenient from the point of view of traffic modeling. Based on what I just said, we could think that it might perhaps be more convenient actually to use the variance because it has this adding up property. I also talked, so you mentioned that that the standard deviation does not capture the skewness of the travel time distribution, which is true, but the value of of standard deviation should capture the skewness through what we just saw. And then I was a bit surprised that you decided to exclude the extreme events. Even though they're hard to model, they're still there. They're part of the travel time distribution that travelers face. And they're in this term that we just discussed, that is the shape of the travel time distribution. But we'll come back to that in an hour or so. So if we accept that this is a theory that we can use, then the next step is to put numbers on the theory to get a value of travel time variability. So far, most of what we have is stated preference studies, and most of them look at the standard deviation. And I think if we had to start all over again today, things might be different. So why do we use stated preference data? Well, it's mainly because we did not have any alternatives when we began doing this. Why did we use the standard deviation? Well, we had theory that suggested the standard deviation, but the theory that suggested the variance based on scheduling didn't exist 20 years ago. We are getting some reveal preference studies. Most of them are from the US, where there are toll lanes, where it's fairly easy to observe the choice between the untolled lane and the toll lane just next to it, and we can get numbers describing the travel time distributions that people are choosing between. For the standard deviation, my sort of broad impression of looking at various reviews is that, and looking at the model, is that a reasonable range for the value of standard deviation is that it's equivalent to about 1 minute, or perhaps a bit less, a minute of travel time. And maybe it's hard to make it more precise than that. But I'd like to talk a bit about stated preference studies. So this is an example of one question given to stated preference respondents. So they have been interviewed about a recent trip. So they have fresh in memory when that took place, how long it took, what the conditions were. And then they have to look at sometimes 30 or 40 choice situations like this, read all the numbers, integrate all the information, work out how good is alternative A, how good is alternative B, and then choose the best. Okay, so if you would like to look at it for a few seconds, and then you can decide whether you think you're able to make an informed decision. Personally, I find it really difficult, which makes me suspicious whether we are really measuring the preferences that we like to measure using this kind of exercise. And we know that when we dig deeper into the data we get, we see all kinds of deviations from rational behavior, which we still don't know how to deal with and get proper valuations out of it. Oops. So in general, what we find is that when we look at stated preference data, then we get results, so we can compare different experiments, and then the results that we get depend on the construction of the experiments in ways that contradict the underlying theory in the scheduling models. So there's something wrong. Either we reject the theory or we reject the data, basically. And we like the theory, I do anyway, quite a bit, because it's simple and captures the basic elements that many people think should be in such a model and not more. So so we hope that we have the fundamentals in the scheduling models. We also hope that what we have in the behavior that we have in reality is about rational, which means that we don't have problems integrating that into cost-benefit analysis, which assumes that people are rational, more or less. Then looking at the stated preference experiments we've just seen, they're pretty hard to digest. And even if people were able to digest these questions, there's always the issue that they might not be willing to make the effort because it's all just hypothetical. They can say whatever they want and there are no consequences. So to be a bit brutal, I think maybe the main attraction about stated preference experiments is that they're comparatively cheap and they're easy to analyze. So if we compare that to RP studies, it's a lot more complicated to get data, and RP data are a lot more complicated to model. But perhaps we need to be a bit more critical about stated preference experiments. So real preference data were more or less abandoned many years ago because travel time and travel costs are correlated, so it's hard to identify the value of time from such data. But that was 20, 30 years ago. Now we can have much more data. We can have huge databases of GPS traces tracking individual vehicles through networks, and we have choice models that are able to handle complete networks and not just a few routes. So we are in a completely different position now than we were in the past. So perhaps it's time to invest again in analyzing real preference data. Then I was asked to say a bit about freight transport, and it was a good prompt for me because, like many other people, I tend to forget freight, which is bad because it's clearly important in the real world. So I think the basic framework of scheduling preferences can be applied to freight as well. And we would get the same kind of results in terms of what the unit of measurements should be. Measuring values from freight is more complicated, certainly if we do SP, stated preference, because there are many agents involved in making choices concerning freight transport. For individual travel, there's the traveler. We can just talk to the traveler, so that's easy. But in a freight transport chain, there are many decision makers, and it's not clear where we should, who we should talk to get the full value that we're after. I think that the case for using real preference data on freight looks quite good, because we have trucks. We begin with trucks. I didn't do a survey, but I would guess that most companies nowadays actually log their vehicles, and they also know what's in them. So it should not be that big a problem to get databases with actual trips, actual timings, actual travel times, and information about what's in the trucks. And then we can, as a beginning, back out the value of time from such data. If we're able to measure the travel time variability on different routes, then we might also be able to back out the value of travel time variability from such data. There's still the problem whether the behavior revealed by trucks reveals all the priorities of the firms involved, but it has the advantage that it's actually real behavior. So in conclusion, we can just work with what we have, as you did in the Netherlands. So we have units of measurements, we have valuation studies, we have some numbers. So we can try to, I think we should try to move away from stated preference data and try to exploit big data to get better sense of what is going on and better values for travel time variability, but also just better traffic models that use real data to a greater extent than happens often. And then the final thing is, I think, even though we have lots of uncertainties, I think we should include travel time variability in cost benefit, because we know it's there, we know it's important, we are able to put reasonable numbers on it. So that's the neutral option, the neutral thing to do. It's not to just ignore it. Okay, thank you.